Welcome back to ECE 220. This is the second week of class, and a lot of things now start to become official. The first week was sort of getting us back from our summer vacation mode, and today homework number 1 is due, and that's due through mastering at 11:59. Hopefully I have that set for 11:59 Tucson time. Sometimes it automatically resets to New York, so if you at New York's time, and so if you look at that and you go, oh, I'm 2 hours over, what? Just let me know and we'll try to make that occur based on Tucson time. I did try to create a PSpice tutorial video, and that's available. I've created a module inside D2L on the content page, and there's material relative to PSpice on that. And in particular, it's capture, but you can put that on your machine if you want, or you can use the machines over in ECE 232 in that lab if you want to run your PSpice. You won't have to do that for the tutorial video. You're really just going to have to watch that by Friday as the due date, but your homework for PSpice will be due next Friday, Friday the 13th. So there is a PSpice homework that you'll need to create, and I basically walk you through the first half of that in the tutorial video. If you want to follow along with the homework, you might have that available as I'm trying to step through the tutorial explanation that you're supposed to watch this week. Office hours this Friday have been modified slightly. They've been slid an hour earlier. I have to attend something that starts at 11. Just as a heads up, I won't be in my office at 11 on Friday. I'll try to immediately get over there and then immediately leave so I can get back to the student union by 11 on Friday morning. The orientation labs begin next week. You physically need to go over to ECE room 311. If, depending on your particular section, that will be either on a Tuesday, Wednesday, Thursday, or Friday. And what did I say? Are those from 1 to roughly 4, 1 to 3:50? Those are your lab times. You have to determine where you are day of the week based on the section that you have enrolled in. There is a group B, that's section I, that will begin the following week for your lab orientation. Homework number 2, as I had indicated before, these homeworks are just going to be routine now. Every Tuesday you'll have one due. Homework 2 is due next Tuesday. And in that same week you have your PSpice, and in a few weeks' time, I'm just trying to get this on your radar. Exam number 1 is on a Thursday, the 26th of September. You have a few days, a little more than 3 weeks, but I want you to be thinking about that, and the material on that will be homeworks 1, 2, and 3. Today I decided let's just stay in chapter 2 for one more day, sort of clear our heads from the long weekend and get back into Kirchhoff, and this is trying to help us better understand KVL and KCL, and we'll do that by examples, and we'll also illustrate another concept, which is, I can actually find the voltage drop across 2 nodes in my circuit if I want to, and those nodes don't have an element between them. That now allows us to do KVL relative to an open circuit or an air gap. And I might just say KVL with an air gap. And that will become clear, I hope, as we work through it. And in fact, that air gap is our voltmeter. We're going to be measuring the potential difference between 2 points in a circuit, and we need to now analyze what we think the voltmeter should be giving us. displaying to us so that we can anticipate whether we are interconnecting things right or if our analysis has been done properly. Example 1. This one should be fairly straightforward. Obviously, I'm not really wanting you to do this at home immediately, so I leave some things blank. Let me fill in some of the details. Let's say that this voltage across that current source, is that an independent or a dependent current source? It's a circle, so it's independent. And I'm not even giving you what the value is for that current source. And let me give you the voltage dropped across that resistor. With those three voltage values indicated, or those voltage drops across the appropriate elements, can you now find the remaining elements' voltage drops? And you should be able to do this really by inspection without doing too much or expending too much energy. Do you see a particular voltage drop that you can immediately sort of write down? Can you find the voltage drop across that top current source immediately? No, there's too much unknown yet to do that. So that one we have to work our way towards. But can we find that first horizontal on the left resistor, the drop across that based on what's been given to us? Yes, now we basically run up 70 flights of stairs. If each flight of stairs is 1 volt, let's say a step, 70 steps, then we can think of maybe a little bit better than 70 flights. Whew. Okay, so 70 steps we go up, then we go across so many more, or go down so many more, and then go down 25. What's this drop then to get us essentially down from 70 that we went up on the left resistor? Do you see that that's X plus 25 to give us 70? Or this now needs to be 45 volts. Now we go up 70 steps, we go down 45, and we come back to where we started by going down another 25. And we could also get the vertical resistor similarly. If we go up 25 steps here I'm sort of doing this mentally. We go down 20, a drop. You see that we would have 5 volts there. And now we have the information that we need. Here we could say, oh, we're going up 20, up 45 in addition. So we've gone up 65. That means we need to go down 65 to get back to where we started, which was over here in that particular virtual KVL analysis. That's what you need to be getting comfortable with, is looking at these circuits and saying, what can I sort of immediately determine based on what's given? And sometimes you can't do all of that without writing some equations down. Let's go to one that involves a little bit more analysis. Here, let me fill in some of the unspecified pieces, which is the resistor on the upper right. That's 3 ohms. We now have a circuit that contains a couple of independent voltage sources. It actually contains a couple of independent or dependent voltage sources. It contains 4 resistors. Those dependent sources actually depend on I, which is indicated, and V sub 1, which is indicated. Relative to this particular circuit, we are asked to find the power associated with the 3-volt source. And I actually gave you a big hint by saying we're going to do a second example using Kirchhoff's voltage law, KVL. Why did I say we're using KVL for this particular circuit and not KCL? If we want to find the power associated with, or if we wanted to find any particular circuit variable in this circuit, a power, a voltage, a current, you might want to be thinking KVL. Why KVL? Why Kirchhoff's voltage law? And now when you're deciding KVL versus KCL, Kirchhoff's voltage law versus Kirchhoff's current law, you're basically saying what is shared or what's in common in pieces or parts of this circuit that I can sort of work from. In this particular circuit, do you see that each of those circuit elements shares the same current or has the same current passing through it? Each of those elements is in series with each other. Somebody might say, well, that's a series circuit. I'm going to write KVL. Or you might say, oh, I is going through every particular element in that circuit. Even though it's indicated down there associated with the 8 ohm resistor, that current is actually flowing everywhere throughout that circuit. And if we wanted to say why KVL, you could sort of succinctly say that all elements are in series, or they all share the same current. And here when I say find the power associated with the 3-volt source, I'm actually wanting you to tell me, is it consuming or absorbing power, or is it supplying or delivering power to the rest of the circuit? And that's not necessarily a given when we have these dependent sources involved. You might think, oh, it's an independent source, it has to be supplying power to the rest of the circuit. Well, maybe not. Maybe it's actually being charged or energized based on what else is going on with the dependent sources throughout. If we want now the power associated with the 3-volt source, what expression are we looking at? Or what formula? Or what 3 letters are you going to text to your friend when they say, find the power associated with that 3-volt source? PSC. Passive sign convention. Based on the passive sign convention, what's the power associated with that 3-volt independent voltage source? We might as well use it. It's labeled. Let's use that I labeling. And if we use that, then the passive sign convention tells us the power associated with that 3-volt source is now 3. That's the voltage times I. And what's the sign here with the passive sign convention? Plus or minus, based on the polarity labels and the current direction. Does the current go into the positive polarity voltage that we've labeled before it crosses all the way through the element itself? Yes. So that means that using the passive sign convention, we would say 3I is absorbed. If it ends up being a negative value, that means we have a negative absorbed, or we have so much supplied. Do we know I? Do we know the current I that's flowing through that series circuit? Is it given? Is it stated? No, we have to solve for it. We now need to find I based on this interconnected circuit of dependent, independent sources and resistors. We now need to find I. And we can do that by essentially writing a KVL equation around the whole loop. And let's just go ahead and start there at the lower left corner to write our KVL equation. Or let me just say complete loop. The strategy that we have now said I like to use, you may like something else, but I'm just going to record the polarity label that I encounter first relative to these sources, and then I will try to use Ohm's law as I go through these resistors relative to the current that I have labeled. And now I'm going clockwise. I'm starting at the lower left. I see a minus sign on that 12, so I now say minus 12. What do I write down next? You might think, oh, minus V1, but that's another unknown variable. Let's just discard that for now and move with what we have. Yes? So again, the question is why minus 12? Aren't we increasing our voltage? It's really just a way to keep track of the signs to be consistent. So in here, I'm sort of saying if another way of thinking of this is as drops. I'm experiencing a negative drop when I go through that 12 volt source. So I say a minus 12 volt drop. Then what's the drop across that 4 ohm resistor? 4 times I. Then I have a 7I drop across that dependent source. Then I have a 3I drop across the next resistor. I have a negative drop, a minus 2VI on that dependent source. That's if I just kind of read the signs as I hit them. I don't have to remember, am I dropping, am I rising? I don't remember if I'm rising or dropping, so I just keep track of the signs, and then they take care of themselves. Then I have a plus 8I drop going from right to left across that resistor in the bottom. I have a plus 3 volt drop going through that independent source. And finally, I have a 6I drop from right to left using Ohm's law across that bottom resistor. So that would be 6I. Did I misspeak? Let me try to write that down. Did everybody, well, if you didn't follow along, now's when you need to make sure it's clear, and I'll get to the question in just a minute. Let's see. Minus 12 plus 4I plus 7I, that was the dependent source, plus 3I, which was the resistor, minus 2V1. Did I misspeak on that one maybe?
Isn't it just 3 ohms? You're saying that there's 3 amps at the resistor?
So this is the question I think is concerning this particular drop. It has an ohm value, or the resistance is 3 ohms. To get the voltage, we use Ohm's law, which is R times I. R is 3. I, in this case, is in fact the I that we've labeled. The drop across this, I is the value we haven't yet determined. And this voltage drop, the way that we just indicated, was 4I. Using the I that we have agreed to use, which was in blue or red. We're wildcats, so we have to use blue and red. Then doing the same thing, this is now 8I, and this is 6I. Again, I is yet to be determined. Question?
So you just, for the 4, you just changed the polarity.
So on the 4, why did you change the polarity? I basically virtually erased that label of V1 and said, I'm not going to worry about V1 until I need to. Right now I said, I'm going to drop, based on what I is telling me, using Ohm's law, that's 4I from left to right, a drop of 4I. And then I will, actually, that gives me a way of determining what V1 is. V1 is the opposite of what I just labeled as 4I. And so if I need V1, I'm going to be able to use that information, Ohm's law. V1 is now minus 4I to give me V1 when I need it. Question? So the question was, why is V1, why are you saying it's a plus 4I going from left to right? That's okay. And I have virtually erased V1 until I need to use it. Was there another question? Yes.
I just wanted to clarify, so are you saying that, like, whichever direction the current is going, we should drop the resistors, like, that way?
Yes, so the question is, wherever we experience, if we've now, depending on how we've assigned our current, Ohm's law, let's say that's 10 ohms, and now if we had a current I here, let's say I sub x, then we know based on Ohm's law that this is going to be dropped across this voltage V is 10 I sub x. And hopefully we've been consistent in applying Ohm's law as we work our way around that KVL equation in the above circuit. I didn't like the circle in black for some reason. Now, we didn't get all the way around, did we? We went through the dependent source. We experienced a negative drop or a rise. Let me finish. Is that okay? And then we'll come back. Then do you see that I have a plus 8I drop from right to left? Then I do go through a drop through that 3-volt source. And finally, I have a 6I drop. And then I'm back to where I started. So all of that is equal to 0. And if you count all of those terms, it should correspond to the number of elements that actually you passed through in that KVL experience. Yes? V1 is unknown. So the question's a valid question. If we already have 2 unknowns, I'm going to pretend that I didn't know that I had a V1 sitting over there vertically. That's basically what I was saying. But you're correct. You could do this either way. I could have said minus 12 minus V1 plus 7i, because the question was, you're going to end up with two unknowns in your KVL equation. Why don't you just keep that V1? And we could have. We should end up with the same result. I just didn't. And so when we have 60 different solutions, we might have 60 ways of coming up with exactly the same answer. And that's fine. What was being asked was, why did you use this instead of minus V1? So that will be what you do tonight at home. You'll work through it the other way and say, oh, I'm getting exactly the same answer. But is everyone okay with the i's and the V1 and the numbers in that KVL equation and how they were obtained? We can now rewrite that, putting all of our numbers on the right, which is now 12 minus 3, or 9. And on the left, let's keep our unknowns. We have 10 and another 10, 28i, and a minus 2v1. Did I do the algebra correct? So all of those i's hopefully will sum to 28. All of those terms containing an I. We just had a minus 2v1, and that's equal to 12 minus 3, where I'm simply adding 12 and subtracting 3 from both sides, which I can always add 0. I can always do the algebra. This is now two unknowns. I can't solve for I can't solve for V1 without some more information. But now the observation is now where you guys were feeling uncomfortable to begin with. Why did you do that? Why is it not V1? Well, let's go back and use it now. Now we can use that information. Now we can use this information which says, and here you could say, oh, I have minus V1 minus 4i is equal to 0. Do you see that I just did kind of a little KVL on my own? What did I do? I just sort of walked around and I said, there's minus V1 minus 4i, and I'm back to where I started. That better be equal to 0. If you don't feel comfortable applying Ohm's Law, saying, oh, V1 is minus 4i. This red now is telling me that minus V1, maybe I should color code this. I guess I'm wanting all my colors that I purchased for the school year. I want to use all of those. We're in college. Sorry. So here's minus V1 minus 4i equaling 0. Or that's V1 is equal to minus 4i. Solving for V1. You can get that however you want, whichever way feels more comfortable to you. But I'm just trying to illustrate different ways of thinking about the same relationship. So now that was our observation. Meaning, now we can relate V1 and I. And we did that by, one way of thinking would be Ohm's Law, which says that V1 is equal to minus 4i. Using our passive sign convention, and the current is now going opposite to what we wanted. We can now use that V1 in there, 28i minus 2 times minus 4i, which is now 28 plus 8, or 36i, is equal to 9. Or I is equal to 9 over 36, or 1/4 of an amp. And that's what we needed in order to find the power associated with our 3-volt source. From the passive sign convention, that was our voltage 3 times I, which was 1/4, or this is now 3/4 of a watt absorbed. Or if you wanted to, you could say that's 750 milliwatts absorbed. The 3-volt source is in fact absorbing 750 milliwatts, or it's consuming from the rest of the circuit 750 milliwatts. Questions on example 2? The passive sign convention says that if we get a positive answer, that's consumed or absorbed power. If the result ends up being negative, that's a negative consumed, which really means it's supplied or delivering. Or the book sometimes says developed. How much power is developed by this 3-volt source? It would be a minus 750 developed milliwatts. Example 3. Now I need to finish labeling this. Suppose that this dependent current source is V1 over 200. That's a voltage-controlled dependent, or a voltage-controlled dependent current source, or VCIS. And why am I saying we're going to use KCL? Why not KVL? Yes? All three elements are experiencing the exact same voltage. They're in parallel. That's basically screaming at you, KCL, KCL, write KCL. That's why we're applying KCL. The elements all experience the same voltage, or all elements.
So with series, the current isn't necessarily.
In series, the current's the same going all through all of those elements. It was all I. Here, the voltage is the same across all of those circuit elements. The voltage dropped across that dependent source is V sub 1. And in fact, the dependent behavior of that is saying, and the current going up is proportional to that voltage dropped. The current going up is V1 over 200. And the voltage dropped from top to bottom across that 2 milliamp source is V1. So let's now find the power associated with all, or with each element in this circuit. And in order to find power, we need voltage and current. Right now we just have one or the other, or none, with these various elements. We know we have 2 milliamps on the right for that independent source, but we don't know V1. If we knew V1, we could figure out that power. If we knew V1, we could figure the power of that resistor. And if we knew V1, we could figure out the power of that dependent source on the left. The upshot is we need to find V1. And we can find V1 by writing a KCL at the top node. And you could write it many different ways. You could say, oh, I want to know what that current is, what that current is, and what that current is. And KCL says, because all of those currents are flowing out, I sum them up and set it equal to 0. What I'm going to do is I'm going to just kind of follow the directions. The dependent source is going in. The resistor's current, I'm going to say, is going down, consistent with Ohm's law and V1, and the 2 milliamp source is going down or out. I'm going to now say N's equal ounce for my KCL. Or, using KCL, with that understanding, I now have N is V1 over 200. And out of this node, that's the node, that's the top node. It's all the same. You could squeeze it into a dot if you wanted to. The current flowing down or out of that node relative to the resistor is V1 over 1,000. And the current out due to that independent source is 2 milliamps. And since I have thousands floating around, let me write 0.002 as 2 over 1,000. These are the ounce. Here I wrote KCL as N's, the sum of the N's equal the sum of the ounce. Depending on your scenario or your particular mood, you may write KCL another way. That's fine, as long as we're all consistent. If we now multiply everything by 1,000, I end up with that relationship from KCL. And that's one equation and one unknown. I can solve that. I now have 4V1 is equal to 2, or V1 is 1/2 of a volt. Now I'm ready to find the powers. I said all of the powers relied on finding V1. Let's look at the 2 milliamp source, the power of that. And it doesn't hurt. You don't have to see everything. You don't have to feel everything. Just write it down if it's not making sense. Give yourself a picture. Here's the 2 milliamp current source, and we've now found V1 across it in that polarity labeling. If that's the case, with the passive sign convention, what's the formula for that power associated with this 2 milliamp source? Using the passive sign convention, is the current direction going through the positive label of voltage before it goes through the circuit element or after? Before, so that means that the passive sign convention says that this needs to be a plus of V1 times this 2 milliamps, I. And V1, didn't we just calculate that to be 1/2? We have 1 milliwatt absorbed. So that supply, that independent current supply, is actually absorbing 1 milliwatt. Let's look at the 2 ohm or the resistor, the power associated with it. Again, we could draw a picture. Here's 1,000 ohms. Here's V1. And what's this current? Or let's just label a current and say it's going down, and that will satisfy Ohm's law. R times I, so that now the power of this 1 k ohm, based on the passive sign convention and the labels that I've indicated, isn't that just plus V1I? The current is going into the positive polarity label before it goes through the resistor. V1, well, let me just write this. And what is I in terms of what we know? We didn't solve for I, but we did solve for V1. Ohm's law says I is V1 over 1,000. Or here is now an alternative power formula. It's V squared over R. You could have RI squared or V squared over R. Another power formula that we've now really just re-derived based on our information. I'm cutting and pasting while you're still writing PSC to your buddies. Passive sign convention. What did we find for V1? V1 was 1/2. We square it, we get 1/4. And we actually now have 0.25 milliwatts absorbed or supplied by that resistor. Absorbed. So now we've had 1 milliwatt absorbed, 0.25 milliwatt absorbed. That dependent source better be supplying this power that we're absorbing or consuming. Let's now look at the dependent source. And that's what the dependent source looks like relative to the labels that we have applied to it. What's the power of that dependent source? Passive sign convention, what's its formula? Is the current entering the positive polarity before it goes through the circuit element? No, it's going into the negative polarity, so the passive sign convention on this one says we have a minus voltage times current. Where the current is V1 over 200. We now have minus V1 squared over 200. And if we wanted to clean this up a little bit, we could multiply by 1, which is 5 over 5 in this case, so that we now have P of our dependent source is now minus V1 squared, well, I should say 5 V1 squared over 1,000. The reason I did that is so I had 1,000 in the denominator, and everything that results will be in milliwatts. Or V1 was 1/2, I square it, I get 1/4, so now I have 5 quarters in my pocket. That's $1.25, or 1.25. This is now minus 1.25 milliwatts absorbed. And our power is balanced. If we summed all of those powers, they would sum to 0. But this could also then say, or the dependent source is supplying 1.25 milliwatts to the rest of the circuit. And that's consistent with what we absorbed or consumed. Let's do a circuit that involves both KVL and KCL. Here, let's find V sub x. And I obviously need to tell us a little bit more information on that. Let's now say that this is 20 volts on the right. A lot of things going on, a lot of labels, a lot of dependent sources, but we can just jump in and hope we can find our way to the other side. The goal is to find that voltage V sub x dropped across that dependent current source on the far right. Go ahead.
Would we be able to just make a calculation at each node and just kind of add the section respectively? Like the first one, just to the right, 20I1.
So we could start looking at each of these nodes, but this is kind of looking like, do you see that all of these are the same polarity? Those are really connected by a wire. They've just been drawn differently than what we're used to, but you could connect all of those with a wire. Now we have 3 meshes. And when you see meshes, a lot of times you start thinking KVL. And if you wanted V sub x, you could say, well, I've got about a minute left on the final exam and I'm trying to find V sub x. I'm going to do a KVL right there. Well, I could do that. I could solve for V sub x if I knew I1. And I'd be done. But I don't have I1, do I? I sub 1. I need to find it. But do you see what the thinking is, the thought process is? In that little mesh, I could solve for V sub x by saying, oh, it's minus 40 I1, starting at the lower left of the green mesh, plus V sub x plus 20. If I just knew I sub 1, I would be done. I could find what V sub x equals. We need to now solve for I1 or some of these variables in order to find V sub x. The green KVL, which is really going to be sort of the third KVL that we use, but let's just say KVL at 3 is now minus 40 I1 plus V sub x plus 20 is equal to 0. Is it clear where that's coming from? In KVL 3. I'm going against I1, so Ohm's law says, oh, that's minus 40 V1. That's Ohm's law applied to that vertical resistor of 40 ohms. I'm going from plus to minus V sub x, and I go plus to minus 20, the drops, and that all equals 0 because I'm back where I started. If I could find I1, I could solve that equation. Well, let's move back. Let's now look at this KVL. That involves an I1. What's that KVL? I'm going to say that that's minus 50 minus 20 I1 plus 18 I sub 2. It is what it is. We just have to accept it. KVL at 1 is now minus 50 plus 20I1 plus 18I sub 2 is equal to 0. But if we were just looking a little bit more ahead, if we would have done this with a KVL, that would have only contained I1 and some other variables. Is that true? So we can cross through branches of our circuit. This KVL number 2, and we'll stop at this point, is minus 50 minus 20I1 plus 5I1 plus 40I1 equals 0. Yes?
Last KVL that you made, why did you do plus
I don't know why I did plus 20. Why did I do plus 20? Because I didn't have the circuit in front of me. That was minus 20I1. Thank you. Please make sure and wake me up occasionally. What I'm trying to do now with KVL around 2, and check my math, it's minus 50 minus 20I1 plus 5I1 plus 40I1 is equal to 0. Or this now gives me minus 50 plus 25I1 equaling 0, or I1 is now equal to 2 amps. And now I know what V sub x is. I can solve for V sub x because the very first KVL equation relied on having I1. We'll pick up there or somewhere close next time.